In this video, we're going to talk about what's called orthogonal diagonalization. In symmetric matrices will play a role as well. So remember that A is symmetric. So a matrix A is symmetric if A is equal to its own transpose. Okay, of course, we need, for this to even make sense, we need A to be a square matrix. So A is an n by n, 2 by 2, 3 by 3, 4 by 4, and so on matrix. So A is symmetric if it's equal to its own transpose. It turns out that if A is symmetric, so if A is symmetric, then A must have real eigenvalues, has only real eigenvalues. In other words, in order to get a complex eigenvalue, A has to be non-symmetric. Okay, so again, that's just a fact that we'll put in our back pocket for now. Another notion I want to introduce is what's called orthogonal. So a matrix P, or O, or whatever, let's say O for orthogonal. A matrix O is what's called orthogonal if the inverse of O is equal to O transpose. Okay, so O is called orthogonal if that's the case. So for example, you could come up with some of these if you had to. Let's say 0, 1, negative 1, 0. It turns out that if you, so let's call this O, it turns out that if you compute the inverse of O, what you end up with is O transpose. Okay, so that's the behavior that we're looking for orthogonal matrices. A slightly more involved or a slightly more interesting one is, let's say we have 3/5, 0, 4/5, 0, 1, 0, and negative 4/5, 0, 3/5. Okay, so let's say that that's our matrix O. It turns out that O inverse is going to be O transpose. And so to compute the inverse, all you really need to do is move this negative up. And so that's the inverse, right? 3/5, 0, and negative 4/5, and the rest will be the same. So it turns out that that's also an orthogonal matrix. And there's a lot that's going on here, but what I want to do is I want to point out a few things. These are vectors. If I think of these as vectors, these should look decently familiar. So these vectors have a few properties, namely that they're orthogonal as vectors. So if I were to take the dot product of these two vectors, you would get 0. Same with the dot product of any two vectors here, say the first and the last. If I were to take the dot product, we get 0. Also, these columns are orthogonal, or orthonormal. So not only are they orthogonal, but they also have length 1. So if I were to add up the sums of the squares, we would get 1. So if you have 3/5 squared plus negative 4/5 squared, you end up with 25 over 25, which when you take the square root, you get 1. Same with this matrix. Now, I want to be very careful. Not all matrices with that property are orthogonal. But if you have an orthogonal matrix, then the columns will be orthonormal vectors. Okay. So we just need to be a little bit careful around complex matrices. All right. That's not true. I'm not sure if that's true, so I should edit that out. And there we go. So what we're going to do then, damn, edit that out. So what I want to know is, let me add one more definition. Let's do it this way. A matrix A is called orthogonally diagonalizable. It is orthogonally diagonalizable if A is equal to P d P inverse for some for an orthogonal matrix P. So for an orthogonal matrix All right. And so if in that case, notice that P inverse must be P transpose, because that's what orthogonal matrices are. So in that case, A can be written as P times our diagonal matrix D times P transpose, because the inverse and the transpose are equal. So what I want to do is I want to give you an example where this is possible, and then it turns out that there's a nice succinct categorization of such matrices. But first, let's do an example. So for our example, I'm going to use the matrix A is 3, 1, 1, 3. And if we compute the eigenvalues, it turns out that, again, I want you to actually compute this, sit down, think about why this is true, but the eigenvalues should be 2 and 4. And we have two eigenvalues for a 2 by 2 matrix, two distinct eigenvalues, for a 2 by 2 matrix, so A is diagonalizable. And then let's think about the eigenspaces. It turns out that E2, the eigenspace corresponding to lambda equals 2, is going to be spanned by the vector negative 1, 1 when you actually do the computation. But what I want to do is I want to make this an orthogonal matrix. So what I'm going to do is I'm going to divide this vector by its length. And in fact, I'm going to make the negative in the bottom as well, just for aesthetic purposes here. So I'm going to make this 1 over square root of 2, negative 1 over square root of 2. Again, by the length of the vector, this is a chapter 5 notion. We didn't spend a lot of time on chapter 5, but what I mean by that is I'm going to take the sum of the squares of the components and then take a square root, and we end up with square root of 2. So I'm going to divide the top and bottom by square root of 2. I'm actually going to divide the top and bottom by negative square root of 2 to get the negative out. Anyways, so that is E2. So it's going to be spanned by the vector 1 over square root of 2, negative 1 over square root of 2. And E4 is going to be spanned by the vector 1, 1. So if you do the computation, you get the vector 1, 1. And in order to make this a unit vector, I'm going to divide this again by square root of 2. It's almost the same computation, just replace the negative 1 here with a 1. But when you square it, you get the same thing, so you still get square root of 2. So this is 1 over square root of 2, comma 1 over square root of 2. And that's going to be the eigenvector corresponding to 4. And it turns out that you can write A as P times D times P inverse, where P is going to be the eigenvector 1 over square root of 2, negative 1 over square root of 2, and negative 1 over square root of 2. And then the second column would be 1 over square root of 2, 1 over square root of 2. And then D is going to be the diagonal matrix, let's see, 1 over square root of 2, negative 1 over square root of 2 corresponded to the eigenvalue 2. So that means the other one must be 4. And so D is going to be the matrix 2, 0, 0, 4. P inverse, it turns out, is going to be the matrix 1 over square root of 2, negative 1 over square root of 2, 1 over square root of 2, and 1 over square root of 2. And you can check that. So therefore, A is orthogonally diagonalizable because this is nothing more than P transpose. Right? So P is orthogonal, and hence A is orthogonally diagonalizable. Okay, orthogonal matrices are very nice because they have lots of properties. The one property that I want to talk about here is the determinant. It turns out that the determinant of, let me write it a little bit better. Let's let P be an orthogonal matrix. Then it turns out that the determinant of P has to be plus or minus 1. And the reason is pretty straightforward. If P inverse is equal to P transpose, then take a determinant of both sides. So the determinant of P inverse is equal to the determinant of P transpose because they're the same matrix. So therefore, everything about them has to be the same, including their determinant. And we know from everything that we've talked about in this class that the determinant of the inverse is 1 over the determinant of the original matrix P, and the determinant of P transpose is also equal to the determinant of P, right? Taking the transpose doesn't change anything about the determinant because you can work along rows or columns equally. Everything's fine. And so therefore, the determinant of P squared, if I take this determinant of P and multiply it both sides by that, the determinant of P squared has to be 1, and therefore P has to have determinant plus or minus 1. So it turns out orthogonal matrices have to have determinant plus or minus 1. That's one of the nice properties about them. All right, and then one final theorem. It turns out that A is orthogonally diagonalizable. If and only if A is symmetric. So it turns out that every symmetric matrix has this property, every non-symmetric matrix does not have this property, and that's a nice and neat criteria for orthogonal diagonalizability.